Hello everyone, my name is Peter Medrano, Christopher Dominguez, Justin Crisp. We are Crydome Engineering and we're here to present to you our senior design project. What we did is an expandable spinal cage for vertebral body replacement. Our advisor was Dr. Benjamin Basil, and we also wanted to give a special thanks to Mr. Ziccarelli and Harry Abduru. Our objective was to design an adjustable vertebral body replacement that can be used for different segments of the spine. All while keeping in mind that we're trying to make a product that's reliable and also a better alternative to traditional spinal corpectomies by reducing the cost. Some of the issues that we have, or some of the issues that are out with traditional spinal corpectomy procedures, is that there are too many amounts of expandable spinal cages for one stiff person. Our objective was to design something that would be able to replace about 75 to 85% of these cages while still making it reliable and overall structurally and with the structural integrity. Okay. The reason why somebody would need to go ahead and replace their vertebrae is usually because of damage. It could be damage caused by long-term osteoporosis, which weakens your bones, or severe spine trauma, which could be things of the nature of car accidents, sports accidents, anything in which your vertebrae is completely fractured and must be removed completely. Okay, and also cancerous tumors will also have that same effect, and where if you have a tumor growing on one of your vertebrae, it would have to be removed completely in order for it not to spread. Next slide, please. As engineers, we have to keep our design intent in mind as for whenever we're designing anything. The design intent in this case is to make something that has structural integrity to withstand all the loads that a body can withstand, or all the loads on a spine. Also, it has to be biocompatible, it has to be safe to use in the human body, and it also has to have the geometric parameters in order so that it fits comfortably in the spine, and also so that it could withstand long-term use. Okay?
To design this replacement, we had to do an extensive amount of research on the human body and what kind of constraints we would have when inserting this cage into it. The region that we're focusing on, because of geometric constraints, would be the thoracic and the lumbar region. We're making our cage so that it can be one cage for any area of that spine. Now, here are some common sizes of each vertebral body. Now, for the smallest one that we have highlighted in yellow is about 1.1 inch in height. So we would have to make a cage small enough to fit that height displacement. Now, for the largest one is at L3, which is in the lumbar region, and that's about 2.1 inches. So it would have to expand to that at least, that amount at least. We also had to take into consideration the diameters of the cage, because we do not want to interfere with the actual spinal column or any other body parts surrounding it. These are the common sizes that we have for the thoracic and the lumbar region. What we plan to do, what we did, was to add separate stamps that we could add to the cage so that we can compensate for those sizes, those change in sizes. We came up with two interchangeable plates, one of a diameter of 1 inch and another one of a diameter of 1.25 inches for the lumbar region. So the forces on the spine are obviously the biggest concern to make sure that this does not fail within the body. The lower the vertebral body is on the spine, the more compression it goes under. We have some standard forces for different types of body movements. So we have standing, flexion, which is like a front bend, extension, which is a back stretch, lateral side bend, and axial rotation. The vertebrae L5 is what experiences the highest amount of compression under the front bend, which is 414 pound force. Now, when walking, you also have to take in consideration that the force increases because the stability is off. And for walking, it's 171% of the standing force. So this is what we want to pay attention to. Ascending stairs increases to 265 of that standing force, and descending stairs is 225% of that standing force. We pretty much designed our cage so that it can meet the requirement of at least 500-pound force that it would go under before any failure can occur. So we needed to design something that can have a minimal amount of area that it can replace all the way up to a higher amount of extension. So we came up with a telescope type mechanism where we have multiple cylinders falling in within one so that it can have a minimum height of at least 1.1 inches. And when turning the ring, we would have a screw that comes up and extends both of the rods and to the maximum height that we desired. This particular design we did not go with though because the top rod we need a required volume for the bone graft to go inside the rod so that it can start fusing with the rest of the body. They fill it with bone cells inside, and if we don't have enough area inside or volume inside, that becomes an issue and it won't fuse. Also, the deflection at the top will be too high and could cause buckling. So we took the components each one by one. This is for our final model. We have the base. We have a 3/8-inch screw with a 24 thread per inch, which allows adjustability, to be very fine, for the amount of height that we're trying to expand. We also added a gear to the ring that will be expanding it, and as we can see here, we have it without the adapter currently for the smaller part of the spine. Once you turn that gear, it will extend what's in the inner cylinder, and we also have these locking mechanisms for once it's adjusted to the proper height, we can lock it and keep it from moving up and down. The adapter is shown here in this part where we can add it in case we need more extension. For the plates, we have the two diameters that I mentioned before, which is 1 inch and 1.25 inches. Now we also had to take into consideration the angle of the spine, the change in angle of the spine. So if we can notice here, we have an 8-degree angle to compensate for that curvature of the spine. So this is what it looks like fully closed. We have it at 1.1 inches, as mentioned. Okay, once we add that adapter, the minimum height of that adapter would take it to 1.77 inches. And once we fully expand the cage with 6 threads engaged, which would be the minimum to allow the maximum force, or for it to be effective, for the threads not to strip. That's 6 threads, and it goes up to 2.43, which exceeds the amount of height we would need to replace the biggest region.
To ensure that our spinal cage would meet the requirements that we placed on it, we decided to go with titanium 6AL4V, which is the titanium that's mostly used in the medical field, and it's compatible with the human body as well. This would ensure that the loads placed on it would be well taken care of and distributed. Here is our final manufacturing. What we did is, since titanium was difficult to manufacture and very expensive, we decided to 3D print the base cylinder, the plate, the screwing mechanism, and the top plate, and we machined the raised cylinder with the threads with aluminum. Okay, when we decided to, do the analysis for the system, we kept in mind the actual body of the screwing part and also the threads. So we found that the maximum force to shear the threads off would be 1,000 pounds roughly. And the torque required to cause the smallest cylinder, the screwing cylinder, which is machined out of aluminum, in our case we use titanium, it would be 270 pounds, 270 foot-pounds. And the force required to, I guess, cause the screw to fail would be roughly about 7,200 pounds. So, placing this in SolidWorks, we wanted to extend it fully to see what would happen to the threads. So we applied the force at the 3 engaged threads at the bottom, which are coming from the base cylinder, and the 3 engaged threads which would be at the top, coming from the top plate of the system. And we found that the factor of safety for that was 2.5, and the von Mises was 1.05 newtons per meter squared. And on this representation, we showed a distributed load on the top plate, and we also achieved a factor of safety for this for 2.03, and von Mises of 1.05 as well. Okay, and this is the base cylinder, and what we did is we fixed the bottom, and we placed the load around the outer diameter of the cylinder, and we determined that its factor of safety was 13, and that its displacement, which due to compression, would be 0.003 millimeters. So, keeping in mind a system, we didn't want it to be too big because we wanted to be able to fit in any placement techniques, like they have A-lift, which is anterior, P-lift, which is posterior from the back, and extreme laterals from the side. We kept in mind that it needed to be small to be able to meet those requirements. So that allowed us to come up with a system that's about the height it is now.
And also one of the nice things about the design that we chose is that it's easy to access from a single angle. So even if you're doing one of the procedures in which you only have very limited space, we designed a tool in order so that you can approach that and not have to have a lot of space in order to spin. Our cost breakdown, we did 2 cost breakdowns. It was dependent on our 2 different models. One model is made out of titanium, which is not the one that we produced for the presentation. And also our model that we decided to use in order so that we could show you something physical. The physical model was made up of aluminum and also made up of plastic that we 3D printed. The costs were relatively low in the aluminum and 3D printed model, mainly because the cost of 3D printing is not very expensive. And a lot of the aluminum in the manufacturing was donated to us by Ziccarelli and the manufacturing location. Just really quickly to talk about global learning. Global learning examines technologies developed by humans for the impact on cultures, politics, economics, and equality of life. It's broken up into 3 categories: global awareness, global perspective, global engagement. One of the most important things that we wanted to accomplish when we set out to do this project was to make something that was less expensive than traditional expandable spinal cages. We did this in order so that we could make it more accessible to people. Traditionally, it could be very expensive to do something of this nature, so by decreasing the amount of overall material and decreasing the amount of overall cost of a traditional spinal cage, which could have a lot of different sizes, hopefully having something of this nature which replaces a lot of those would be able to reduce cost, where we could pass those costs on to different people in the world which would need it. Our timeline, we had a year to go ahead and accomplish this. In January, we did the majority of our research and our research into existing technologies and what are some of the issues with existing technologies and how we can improve on them. And from this timeline, you can see we ended in December, in which we designed and manufactured it, and we were able to go ahead and present it to you all. Next. The division of labor was broken down in such that we can go ahead and have everything distributed evenly, but also while having enough time and things so that we can go ahead and help each other with every aspect of it. And that's it. Thank you very much.
Questions? Dr. Tamonto?
Okay. Classically, how they would manage this would be with steel, with metal frame on left and right to stabilize the whole structure and basically allow the fuse to form. How do you prevent, or what went into your thought process on this design, which is, number one, asymmetric? You don't have structure all the way around the spinal cord, and now all of a sudden when you start applying loads to it, you could potentially have this system walking out of its position?
Well, we actually were in between both using just like the pedicle rods that they usually have to stabilize it, or they also have plates that you can just attach here and then with like pedicle skews as well. We didn't design it, but that's something that if for future work that we would want to design to add to the cage. But definitely we did think about that, and we figured those pedicle rods are pretty much standard and they're flexible, so it still allows movement, but it just helps stabilize the cage. Now, I didn't mention it, but if you notice that the plates on the
It's spikes.
it has spikes, so they allow for the penetration through the vertebral bodies.
That only lasts a little while, because unfortunately with the motion, you'll start to break down the spinal cord top.
I thought that it would pierce through it, and because the
Soft
bony
core.
material, yeah, the bony material inside would eventually fuse to those spikes and would adhere to it. No?
Constant
well,
motion.
Yeah.
It's too much continuous motion.
Oh, okay.
Yeah.
But the rods are definitely something that we would like to add to this design.
The rods, I was going to say something real quick. The rods itself do not have, are pretty standard. Okay. What we designed here is the expandable spinal cage in order to allow for the best fit to replace the vertebrae itself. The rods would be used in order so that it would not allow so much in order so that the fusion could take place. But one of the main things that we're really focusing on was improving the design of traditional expandable spinal cages specifically.
All right. How user-friendly and acceptable and efficient will this procedure be for the surgeon doing the work? And what consideration did you give to that? So it's user-friendliness, acceptability, and efficiency for the surgeon.
You want to answer that?
The surgeon would have different approaches where he can surgically place the cage, and because we have the different screws here on each corner of on each side of the cylinder, the base, and this gear allows rotation directly to it, so it doesn't need like any more area to install in one certain procedure than the other certain procedure. Like you can go anterolateral or posterior, and you still just need that same area, just as long as you can get that key in there and twist that so that it can expand.
Yeah. Also, what you were saying, Dr. Carnegie, is one of the things that we designed for, as far as is to make this a lot easier in order for someone to go ahead and install it. The idea behind an expandable spinal cage like this is you adjust it so that you have a rough estimate of the space that you need outside of the cage, outside of the body. And once you're inside of the body, those extra millimeters that you need to expand it in order to get the perfect fit, you use with some type of key that we actually manufacture over here. It's just a small key that would allow, it looks a lot like a chuck key that would use in something like a drill. And it goes into those gears over there in order so that you can get the last bit of clearance, or you could get that last bit of fit. And it's definitely something that we designed for in order so that the surgeon itself does not have to work so hard to get that perfect fit at the end. So you can make a rough estimate outside of the body, and once it's inside the body, you can go ahead and adjust it so that it fits perfectly. That's the idea behind this.
How long will a typical surgery be?
About 15 minutes. It takes about 15 minutes to open up the patient and insert one of these cages. And recovery time, depending on which approach you take, it takes about 2 days in the hospital if you do the X-lift, which is the fastest recovery time, and it takes about 4 to 6 weeks for you to pretty much start moving and start being more active.
So the therapy period is what, 6 weeks?
Yeah, it could be up to 6 months if they go on a lateral approach, because they do have to cut through some muscles to get all the way to the back of the spine. So that approach is not preferred, but in some cases you have to go through that approach.
Okay, any other questions? Dr. Basil?
Sure. Did you guys do any, I know you did most of your simulations for titanium, right? Did you do any verification of any of the or any of your design itself, your manufactured part? So for instance, did you go back and redesign with
The simulations we did were just mainly for the titanium, since that was going to be a final product, and we prototyped it to show proof of concept.
Right. So how do you know that those simulations are accurate?
We validated them using not only the SolidWorks for titanium, but comparing it with things that we found during our research.
Okay, so how do
Like
you
the
know?
loads that would be placed on the spine, due to picking up books or things of that.
Sure,
nature.
so, but how do you know your SolidWorks specific simulations are accurate?
Tried to validate them by handwritten calculations, but to be honest, we really don't know because it's so dynamic.
Yeah, because it was made out of plastic, and actually the aluminum was a last minute thing because our 3D part failed when we were dyeing it. And since it was plastic, we didn't intend to actually put it under compression testing because of that.
Why not?
We felt that the material would be a lot weaker.
Sure, but at least you can validate your specific simulation, right? I mean, it's not about 100% one-to-one, this is gonna go into the body, but if your simulation is correct with plastic, you can feel more comfortable than just saying, oh, we're not exactly sure. So, anyway, for the future.
Yes, sir.
All right.
I
Any
have
other
a question. Maybe I'm missing something, but you have a device and it is closed, and spinal cord is there. How are you going to make this device go around the spinal cord?
The spinal cord is actually located behind the vertebrae and between the pedicles and the actual vertebrae itself. This will not be touching the spinal cord. This yellow part would be the spinal cord. So yeah, we had to take close consideration to make sure that it does not interfere, because that's actually like the route way where send signals from other part of your body to your brain. So we had to make sure that it does not.
So when they take
interfere.
out the bone, yeah, they're not removing this back piece, the pedicles, and they're just mainly taking out the plate of the spine, the vertebrae.
We took it out for this, but
Yeah, we had to
these
take it out for
actually
this.
stay.
But there would
along
be
with the
there would be
spinal.
bone right here, at least covering the spinal cord.
And then with what we mentioned earlier about the pedicle screws, the rods, that would keep it in place so that it would not move.
So your device is not going to be around the spinal cord at all?
No,
sir.
not at all.
Going to be-
All right, sounds like it, thank you. Well, that brings us to group 6.